Robotic animals and robotic machines have a closer relationship than you may realize. Giant robotic animals could change the way humans see wildlife. Have you ever wondered why nature is so clever? Look no further than these 8 astonishing robotic animals that have dazzled the world. What are these animal robots, and why are they being developed? Today we introduce all of the robots and provide information on each. The bionic kangaroo. Festo has been working hard on its large German lab and its most ambitious bio-inspired robot to date. A robot kangaroo that can't be stopped from jumping around. Because if a bionic kangaroo can jump like a real kangaroo, it needs to regain energy after each jump to continue jumping quickly. Kangaroos in the wild would tire out quickly and they would not perform this action. The animals can hop at high speeds for extended periods because their tendons are used like elastic springs. The legs of the bionic kangaroo are partially charged upon landing thanks to the use of natural elastic spring. The robotic animal only weighs 7 kilograms and is a meter tall, but it has pretty impressive jumping ability. Being able to leap 0.4 meters up and 0.8 meters across, it is also necessary to have internal power source. The high pressure air required by the pneumatic muscles that control the bionic kangaroo's jumping is supplied by either a compact compressor or by storage tank. Lightweight batteries power everything, and the robot's complex kinematic control system prevents it from toppling over. Festo still needs to have plans to deploy a legion of robotic kangaroos. Instead, they are searching for innovative ways to combine electronics, pneumatics, and intelligent ways to recover energy lost during an industrial automation. 𝗵𝗎. MIT's brand new little cheetah robot is bouncy and light on its feet, and it can move like a gymnast of the highest caliber. The ability of the 4-legged powerback to bend its legs wide allows it to walk both right side up and upside down. The robot can trot across rough ground at speed that is twice as fast as a person can walk. The robot barely weighs 20 pounds, and if it is kicked to the ground, it can swiftly get back up by swinging its elbows in a kung fu-like motion. It can rapidly get back up if it's kicked to the ground. Researchers believe that the little cheetah is designed to be nearly indestructible, which means that even if the backflip goes wrong, it can get back on its feet with little harm. In other words, the 𝗵𝗎 can survive. The researchers assembled 3 electric motors already on the market to create the 3 identical low-cost motors for each robot's legs. 3 identical electric motors power these motors. The little cheetah is simply a scaled-down replica of its ancestor, the Cheetah 3. The Cheetah 3 was a giant, dangerous, heavy robot that frequently required being held down with a tether to protect its high pace and custom-made components. Robot Dragonfly. The world's most sophisticated and portable flying drones, made by TechJet, can be used for research, gaming, personal photography, and filming. TechJet's expertise results from years of study and experimentation into microflight solutions with a wide range of reconnaissance needs. This led to the company's expertise. As it flies or hovers through the air, this lightweight robotic insect gathers information and transmits it to its base. The TechJet Dragonfly is the pilot product of the company, and its name comes from the insect itself. The company is a spin-off of the Robotics and Intelligence Machines (RIM) department at Georgia Tech. Within this department, Dr. 𝗕𝗏𝗏, the founder of TechJet, led and collaborated with other engineers to design and improve flight mechanics, controls, and avionics in the hopes of developing the smallest and most sophisticated flying drone. The TechJet Dragonfly makes its design cues from real-life master flyers, dragonflies. It has unique flight characters that are native to insects, giving it superior flight performance in comparison to conventional flying systems such as helicopters, airplanes, and quad rotors. Octobot. Despite recent advancements, soft robots still require a connection to complex robots' power and control systems. New ways of making soft robots, including soft versions of these essential parts, are needed to reach their full potential. A monopropellant fuel source on board the robot is catalytically decomposed due to microfluidic logic controlling the fluid flow. When the fuel breaks down, it releases gas. Downstream of the target sites, this gas expands fluidic networks, which causes them to migrate. The robot's shell and microfluidic logic are made using soft lithography and injection molding. The onboard fuel storage, catalytic reaction chambers, and pneumonic actuator networks are built using multi-material integrated 3D printing. Numerous orders of magnitude, from the micro scale to the macro scale, are covered by fluidic and elastomeric designs for function. This architecture paves the path for entirely soft, self-sufficient robots thanks to their integrated design and fast production procedure, which permit the programmed synthesis of numerous materials within the architecture. 𝗕𝗏𝗏. Electronics and pneumatic valves have been installed inside the waterproof head of the 𝗕𝗏𝗏, designed as a demonstration by Festo AG. The fish measures about 100 centimeters in length and weighs about 4 kilograms. Silicone makes up its thin, while laser-sintered polyamides makes up for its internal ribs. The valves that control the two fluidic muscles for the tail and the two more for steering are provided with electrical power by lithium polymer batteries. Synthesizing movements with accuracy of about 1 degree is possible with the humanoid robot. Because of its 10 festofluidic muscles on each side of its torso and 16 smaller prototype muscles on each wrist, the robot can pick up and hold an object weighing 1 kilogram in each of its hands. When precision and large amounts of these rigid force are required, hydraulics and servo motors are excellent power source choices. These technologies are less desirable for use in circumstances that require a light touch and some degree of compliance. These latter requirements have served as a driving force behind the research currently being conducted on artificial devices that stimulate the action of human muscles. Pneumatic muscles are a common type of artificial muscle currently being researched and developed by scientists. They function similarly to inverted bellows, drawing in as they expand their volume. The force they apply relies on a degree of inflation and operating pressure. Even though they can be lightweight, they still can transfer the same amount of energy as pneumatic cylinder of the same volume operating at the same pressure. 𝗕𝗏𝗏. 𝗕𝗏𝗏 has a height of 2 feet and weighs around 55 pounds. You should add 10 additional pounds for the creepy arm with the grip or head hand at the end. The self-contained robot can function for up to 90 minutes on a single charge and does not require a tether. Even though it might not be as endearing as Cal Worthington's dog Spot, Boston Dynamics' newest quadruple robot 𝗕𝗏𝗏 is designed to find a place in your household. BD's existing big dog range of robotic pack animals inspired by the creation of 𝗕𝗏𝗏, a more compact version of the big dog. The 𝗕𝗏𝗏 will be provided with sensors for navigation, guidance, and perception. These sensors will enable a degree of autonomy for the device. Nevertheless, it will still require its operator to provide input for its higher level tasks. In other words, it will be nearly Rosie the robot later, but it will be able to undertake a range of chores around the house. The difference is that the 𝗕𝗏𝗏 operates in a significantly gentler manner. Instead of tossing bricks, the 𝗕𝗏𝗏 uses its arm to load glasses into a dishwasher, throw rubbish into a waste bin, and right itself once it has fallen over. 𝗕𝗏𝗃𝗃𝗃. The ultra-light flying object is known as the 𝗕𝗃𝗃𝗃, modeled after a dragonfly, was awarded the title of world record holder for the most giant flying robotic insect on one page. The 𝗕𝗃𝗃𝗃 is a highly lightweight flying object. The 𝗕𝗃𝗃𝗃 can fly in every direction and perform even the most complex flight maneuvers, just like a bird that served as its inspiration in the natural world. Because it can move each of its wings independently, the 𝗕𝗃𝗃𝗃 can quickly accelerate, turn sharply, and even fly in the opposite direction that it's facing. This reveals that, for the first time, there is a model capable of mastering all of the flight conditions of an airplane, a glider, and even a helicopter. Even though that is a highly integrated system, it can be controlled with relative ease and clarity using a smartphone despite its inherent complexity. In every aspect of the flying object, the principles of ultra-lightweight construction have been implemented. The scale model of the Dragonfly has a wingspan of 24.8 inches, 63 centimeters, and a body length of 7.3 inches, 44 centimeters. However, it only weighs about 6.2 ounces, 175 grams. The wings are made of a frame of carbon fiber and a thin covering of foil. During the flight, the intelligent kinematics dampens vibrations and maintains the aircraft's stability. E-motion butterflies. The bionic butterflies show how complex future production topics like functional integration, ultra-lightweight construction, and, most importantly, real-time optimized network communication between different systems can be shown. In the Bionic Learning Network, flying is a common theme. The people who made the bionic butterflies used what they had learned from previous bionic projects and the so-called e-motion spheres to make them. They combine a small size and lightweight of artificial insects with the coordinated flying of a group. An external, well-connected guidance and monitoring system ensures that each flying object can move safely and independently in 3 dimensions. Communication and sensor technology is used to make an indoor GPS that controls the butterfly's movement so they don't run into each other. The combination of integrated electronics, external camera technology, and a host computer ensures the stability of the process. Artificial butterflies have electronics built into them to make them fly much like their natural counterparts as possible. These control each wing separately and precisely so that the fast flight can be changed. If you liked the video, check out this video, 15 coolest gadgets you must see.